Okay, thanks for coming. We have a very exciting, I would say, session for the energy astrophysics seminar today with two also local speakers. I'm very happy to introduce now the first one, Finnish speaker Kosec. Many of you probably already know him. So Peter obtained his PhD at the University of Cambridge, the other one, under the supervision of Andy Fabian. He then continued as a postdoc at MIT, working with Erin Kara and the Chandra HETG group. He joined SAO just 1 year ago as an Einstein Fellow. And broadly speaking, his research focuses on the accretion disk winds, which is studied with high resolution X-ray spectroscopy. And today he's talking about a very exciting result, I think, reviewing the physics of accretion disk winds with the Hercules X-1. Okay, I remind you that we are recording the seminar. With this, the floor is yours.
Thank you for the introduction. Can you still hear me well?
Yeah.
Okay. So thanks for the introduction. I'll be talking about accretion disk winds. And specifically today, I'll be presenting one very exciting and very fascinating X-ray binary called Hercules X-1. And I will argue that this X-ray binary reveals the physics of disk winds in ways where you really cannot access anywhere else. So to introduce disk winds in a bit more detail, disk winds are wide-angle outflows launched from disks of accreting systems that have been predicted and observationally confirmed in many kinds of accreting systems. This includes active galactic nuclei and tidal disruption events, so accreting supermassive black holes. It includes X-ray binaries that this talk is going to be about, so accreting stellar mass black holes and neutron stars, and even accreting white dwarfs. These winds come in many flavors, come in with a very broad range of velocities, from outflows with velocities of just hundreds of kilometers per second to outflows with velocities of tens of thousands kilometers per second. So this is a huge zoo of different kinds of velocities and properties, flavors. And there is a large range of possible theoretical launching mechanisms, how these outflows can exist, that include radiation pressure, either on electrons or on specific UV line transitions, or magnetic forces, or even just thermally. These winds are of interest because they have the potential to carry away a large fraction of the originally infalling mass. So specifically in X-ray binaries, they've been shown observationally that they can carry away most of the mass that was originally infalling onto the compact object. So they can heavily modify the accretion flow of these systems. They can modify the amount of accreted mass by the compact object, and they can modify the long-term evolution of these X-ray binaries, as we will hear in the next talk by Monica. And secondly, some of these winds have huge velocities of tens of thousands kilometers per second, and therefore they carry huge kinetic powers. If this kinetic power is sufficiently deposited in the vicinity of the compact object, it will strongly modify this vicinity. So for this reason, high velocity winds from accreting supermassive black holes are strong candidates for driving AGN feedback in galaxies around in our universe. And then thirdly, by measuring the outflow elemental abundances, we can learn something about the material that is falling onto these black holes and compact objects. So specifically in tidal disruption events, by measuring the abundances of outflows in these systems, we can learn about the composition of the stars that have been disrupted by these TDEs. And however, despite studying these phenomena for decades now, we still are lacking a lot of information about them, like what are the specific launching mechanisms in these systems that produce these phenomena. And secondly, we still struggle to accurately quantify what are their energetics and the mass outflow rates, and therefore what is the actual quantitative impact these outflows have on their surrounding. So one of the problems that we have is the way we study them. And basically when an outflow is launched from the disk by some physical mechanism, it is ionized by the inner accretion flow hard X-ray radiation, and therefore it emits and absorbs at elemental transitions across the electromagnetic spectrum. And many of these transitions are in the X-ray band. So the X-ray band is a good energy band and sometimes the only band in which we can study the properties of these winds. If the outflow crosses our line of sight towards the X-ray source, it will absorb some of the original X-ray continuum, producing an absorption line spectrum. This absorption line spectrum is very powerful because it is relatively straightforward to interpret, and so we can learn something about the outflow physical properties. But it has one big disadvantage, that is that we are only probing the properties of the wind at the point where it is crossing our line of sight towards the X-ray source. So we're blind to the rest of this 3D structure of this outflow that is out of our line of sight. And so it's difficult to infer properties like the global mass outflow rate, the global energetics, which is what we really want to learn about this outflow. Some of the matter out of our line of sight towards the X-ray source will remit some of the X-ray radiation into our line of sight, producing instead an emission line spectrum. Then this emission line spectrum encodes this full 3D information, but this is also much harder to interpret because we then need to model this full 3D structure. And secondly, often these emission lines are much weaker than the absorption lines. Here on the bottom right, I'm showing an example of a very high quality disk wind spectrum of an X-ray binary, where you can see the absorption lines are very strong, whereas the emission lines, if they're there, they're much weaker. So their modeling is much harder and can be degenerate because there are other sources of emission lines that don't come from disk winds, like relativistic reflection from disk itself. So we have a problem, either we study absorption lines or emission lines, they both have some disadvantages. A second big issue in understanding the physics of these disk winds is measuring the volume number density. Through modeling of these photoionized lines, we can determine properties such as the velocity from the line shift, column density, so how much of the outflow there is along our line of sight from the line optical depths, the ionization parameter, the temperature from the line ratios, but almost never the volume number density. However, this is one of the most crucial parameters because it comes into the definition of the ionization parameter Xi. Basically, if we know the number density, then we can determine the outflow distance from the ionizing source. And so we can place the outflow precisely on a map, and we can determine what is its launching mechanism. Secondly, the number density comes in the second equation for the total mass outflow rate. So to determine the total energetics, we should also know number density, and relatively precisely too. And this is very hard to measure. There are some density sensitive lines in the X-ray band, but they're very weak. And this measurement has only been done once and is still debated after like 2 decades. So in this talk, I'll be presenting Hercules X-1, which is a very unusual X-ray binary. And I'll argue that Hercules X-1 allows us to break both of these problems and solve them. So Hercules X-1 is a neutron star X-ray binary. It's one of the first X-ray sources actually discovered. It was discovered in the 1970s with the Uhuru satellite. And here's actually one of the original citations by Harvey Tannenbaum et al., 1972. And it's very fascinating because it shows this 35-day cycle of high and low flux states that has been repeating for nearly the past 50 years. So each cycle has these 2 high states separated by 2 low flux states. And this cycle has been studied over and over. And the interpretation of this source is that it's an almost edge-on system where the disk is warped and is processing every 35 days. So there are periods of time where we can directly see through our line of sight to the inner accretion flow and the neutron star, which produces most of the X-ray radiation, and we see a high state. But there are other periods of time when the warp disk processes across our line of sight and obscures the inner accretion flow, and then we see a low state. Here is a simulation of what this precession could look like. So you can see that most of the time, some part of the disk is obscuring the inner accretion flow and the neutron star, and so we see a low state. But there are brief periods of time when this is uncovered and we see a high state. So what we can conclude from this is a source where a sight line through the accretion flow and above the disk is changing over time. It has a varying sight line. That means if there is a wind in the system, our sight line is intersecting different parts of the wind, specifically at different heights above the disk at different times. And turns out this source actually does have an accretion disk wind. in 2020, we reanalyzed some archival XMM mutant data, and we detected absorption lines in the XMM RGS spectra, which are slightly blue shifted and indicate the presence of an accretion disk wind. And what was really important is that the wind was detected in 8 observations and seemed to vary very rapidly and strongly. And our interpretation is that this is not because the system itself is changing. It's just our line of sight is changing over time. And specifically, it's changing and sampling different heights above the disk. So this way, we have a unique opportunity to understand the wind vertical structure by studying it through absorption only, which normally would be completely impossible. So to use this opportunity, we propose to and carried out a large campaign with XMM Newton and Chandra, basically sampling how the wind properties change during a single high state, how they change with precession phase and by extension with height above the disk. And here are some of the observations just focusing on narrow energy bands around the strongest absorption lines of this wind. And the disk precession phase is increasing upwards. And what we can see at low precession phases, the wind absorption lines are strong. And as the precession phase increases, the lines go weaker until they basically disappear. What this really means is that low precession phases, this is just after the disk has uncovered the neutron star from our point of view. That means we're sampling low wind heights above the disk. But progressively at greater precession phases, we're sampling greater and greater heights above the disk. And that means the wind is weakening at greater heights above the disk, which makes sense. So doing this more systematically, we split all of the observations that we had into 28 epochs and analyzed all the wind absorption lines at once with photoionization models to determine more physical properties like the column density and the ionization parameter of this wind. Well, what we see is that at low precession phases, so again, when we're sampling low heights above the disk, the wind column density is very high, but drops very hard as the precession phase increases until by 3 orders of magnitude, until it's barely detectable. So the wind is really weakening with height above the disk. This is in line with the statistical studies of X-ray binaries, which found that strong disk winds are only detected in high inclination X-ray binaries. So in those systems, we're really sampling the wind very close to the disk. We also see an evolution in the ionization parameter, but this is less pronounced than the column density evolution. And now, since we have measured these physical parameters, we can start to make some inference on the wind location and its distance from the ionizing source, making some assumptions on how these properties evolve. But there's a second really important thing here is that we can also model how the warp disk is processing with time and with phase. So we can basically say where our sight line should intersect the warp disk and at which height above the warp disk. So basically we can place this wind both vertically and horizontally, creating for the first time a 2D map of a disk wind. So here in the y-axis is literally the height of the wind above the disk. On the x-axis is distance from the neutron star. And on the left, the color scale is the column density. On the right is the ionization parameter. So what we see is a wind that originates somewhere where we would expect a thermal disk wind to originate. So it's consistent with being a thermal wind, rises from the disk. And as it expands into space, both the column density and the ionization parameter are decreasing. So this is a really powerful measurement because it allows us to make direct comparison with 3D hydrodynamical simulations of disk winds in order to constrain what is the actual launching mechanism, what is the 3D mass outflow rate and energetics. So this really solves this dilemma between using absorption versus emission and running into issues with both of them. The second issue that I mentioned before was the problem of measuring the number density of the wind. Even after spending over 500 kiloseconds of time on this source, our constraints on this number density are very weak. Basically, we have 3 or 4 decks of space that is formally allowed. And so the number density is basically unconstrained. And this is really weakening our constraints on all of these physical quantities that I mentioned before. But I'll argue that Hercules X-1 can actually solve this problem also because it is an X-ray pulsar. It is powered by a highly magnetized neutron star that rotates every 1.24 seconds. And this means the magnetic field of the neutron star disrupts the inner accretion disk and channels the matter to accrete onto the magnetic poles of the neutron star, onto a structure that we call an accretion column. This accretion column has a very non-isotropic X-ray radiation, and since this whole thing rotates every 1.2 seconds, the X-ray radiation from this source is pulsed with a period of 1.2 seconds. So this wind, which is located at much greater distances than this magnetic structure, is illuminated by a periodically varying X-ray source. So it responds to this periodically variable X-ray source by adjusting its ionization state to return back into the equilibrium. And what's very powerful is that this recombination time of plasma in this wind is inversely proportional to the number density of the wind. So by observing this response to the pulsation of the wind, we can start constraining and measuring the number density of the wind. Here, I'm just showing as an example, this is one of the original X-ray pulsation light curves from Uhuru from Tannenbaum et al. 1972. So we can actually simulate how this photoionization response will look like. We use the time-dependent photoionization called TIFO, which was just recently developed by Rogantini et al. On the top panel, this is just the pulsation light curve of Hercules X-1. And on the bottom panel is the column density in the strongest disk wind absorption plane, which is iron 26. Basically, what happens is as the X-ray flux increases during the pulsation, some of the iron 26 atoms are fully ionized into the iron 27 state. And so the column density goes down. As the peak goes through and the X-ray flux decreases, some of the atoms recombine back into the iron 26 state. So the column density goes up. So, but this depends, how much this changes depends really on the number density of the plasma. For very low densities like 10 to 9 or 10 to 10 per centimeter cube, basically the plasma is not dense enough to respond quickly. And so the changes are very weak, basically unobservable. For intermediate number densities like 10 to 11 centimeter cube, we see a response, but it's clearly delayed with respect to the X-ray pulsation. For even higher number densities, this response is strong and it's almost immediate because the plasma is just dense enough to immediately respond to these changes in flux. So now what's left to answer is, can we actually detect this in real data? Basically, what we're trying to do is detecting changes on time scales of 1 second, which would be very hard in a regular X-ray binary. But this is a periodically varying X-ray binary, so we can fold all the pulsations on top of each other, performing a pulse result analysis. Just what's done here. So we took the best quality XMM Newton data, split it into 10 bins by pulse phase, and then analyzed and measured the column density in the iron 26 line. And that's exactly what we see. We see an anti-correlation between the column density with respect to the time-varying X-ray flux. So we see that as the X-ray flux goes up, some of the atoms are ionized, column density goes down, and then vice versa. So we see that the wind is responding on these 1 second time scales to the pulsation. Instead of looking at just one line, we can also look at all lines at the same time and measure instead the ionization of this wind. And we see the same thing. The ionization goes up as the X-ray flux goes up, as we would expect. So what we observe is that this wind is responding to the flux changes, and it's doing this promptly, which constrains its number density to be at least 10 to 12 per centimeter cube. Of course, we would much rather like to have more than just a limit and most ideally a direct measurement of this number density. But for this, we need a better telescope than XMM Newton. And this telescope actually exists. It's been launched last year and it's called CRISM. So this telescope will offer us more than an order of magnitude improvement in spectral resolution in the crucial iron K band between 6 and 7 keV. Here is just a comparison between this best quality XMM Newton observation and a brief simulation of a GRISM observation. With this much improved data quality, we can do precision measurements of this disk wind in Hercules X-1, and so precision measurements of how it responds to this X-ray pulsation. So this is what we proposed to do, and this observation was approved and actually carried out just last month. So this is not just the future, but it's actually the present. So what we're hoping to do is directly measure this wind density at different heights above the disk. This will very precisely constrain our positions in this 2D map of the disk wind, basically constraining and determining the wind mass outflow rate in 3D, the wind energetics, and the wind launching mechanism. So just to very quickly conclude, Hercules X-1, I think, is a unique source, and it's an ideal laboratory to study the physics of disk winds. We leverage this disk precession to study how the wind vertical structure looks like, and started to produce constraints on its 2D structure. Secondly, we leverage the X-ray pulsations of this source to start putting constraints on the number density of this disk wind. But a combined campaign that led by Grison, which was performed just last month, is gonna be able to push us even much further and allow us to directly measure this wind number density in 3D and over a range of heights, which will allow us to determine the wind launching mechanism and the energetics. Thank you.
Really interesting. Questions from the audience?
I was curious about how many discs are warped. Do we know that number?
So we know of a few. There are X-ray binaries in the Magellanic Clouds, which we think are like this. But there could be many more, only not all of them are inclined to us so edge-on that we actually see this kind of long-term flux evolution.
Right, thanks. So I want to know, as you see the changes of the orientation of the disk, did you have any supporting evidence from the absorption line winds to give the kinematics information of the range and to see more phenomena?
Yeah, that's a good point. Not with the current, or not with the previous data that we had from XMM, Newton, and Chandra, but with Grison, this should be possible. It should give us more, like the kinematic information should be complementary to this.
And what's the typical value of the range velocity or velocity dispersion?
Yeah, the velocity is relatively low. It's 200 to 1000 kilometers per second. The width is maybe 100 or 200, as far as we know. We'll know much better now with Grison.
Thank you. Any question online?
So you said that the emission lines in these systems come from kind of spatially, geometrically different place. But are they expected to overlap the absorption lines? And how might that affect your measurements?
Yeah, this can be a big problem in principle because they should lie close to each other if the velocity is low. But fortunately for us, I think in most X-ray binaries, emission lines are much weaker than the absorption lines. So this correction isn't too large. But in the most ideal case, we would like to do a simultaneous analysis of both.
Hi, thanks for an interesting talk. As someone interested in AGN feedback, how well should this translate to black hole accretion disks?
Yeah, of course. Yeah, you cannot do this kind of analysis for AGN, but maybe you can do it statistically.
I mean the model. Do you think it would translate if you just scale masses and accretion rates?
If the launching mechanism is the same, I think it should scale. But I don't know if thermal winds are a big factor in AGN feedback rather than radiation pressure.
Okay.
Assuming this is a thermal wind. Yeah. I think it should scale.
Any more questions?
Online? Maybe there was one online, I think.
I didn't see.
No?
I saw somebody with a raised hand.
So we cannot see who's asking online, but please speak up if you have a question. Dennis, did you have a question? No, okay. Never mind. More questions? No, if not, let's thank Peter again. Okay. And certainly mine, meanwhile, I'm going to introduce our second speaker, Gallegos Garcia. She's the junior faculty at the Harvard Society of Junior Fellow at the Harvard Society of Fellows and then IPC Fellow at the CfA. She earned her PhD from the Northwestern University, where she was advised by Professor Vicky Calogera, and she earned her bachelor degree from UC Santa Cruz. Monica is interested, broadly speaking, in binary evolution, massive stars, and black holes. And today she's talking us about giving insight into the formation of binary black hole mergers towards a comprehensive study of binary evolution. Thank you, Monica.
Hi, everyone. Can you hear me okay?
Yeah.
So a lot of my work has been surrounding trying to understand the formation of merging binary black hole systems. And in general, there are two broad categories for how these merging binary black hole systems can form. One of them is through isolated binary evolution, and the other is the dynamical evolution. In the dynamical evolution of merging binary black holes, the idea is that you have a lot of black holes in a very dense environment, like a globular cluster. And every now and then, these black holes will get so close to each other that they will become bound and eventually merge. There's also isolated binary evolution, where you start with two massive stars that are orbiting each other. And one by one, they collapse to form a black hole. But interactions during the evolution can help the binary reduce its orbital separation and lead to a merger within the age of the universe. So my work has involved isolated binary evolution. So I wanted to give you all a sense of the types of physical processes that we have to model in order to study binary evolution. So here there's two massive stars orbiting each other. And as these massive stars age, they expand. And it can expand so much that it crosses the Roche-Loeb radius, and mass begins to be transferred from the more massive star to the less massive star. And eventually this one forms a black hole. So the evolution, once the black hole is formed, the evolution following once the black hole is formed is really what I have been focusing on. The two different pathways that can happen is something called a common envelope. And the idea here is that the massive star gets so big and the black hole is so close that the black hole plunges into the center of the star and spirals inward. And the general thought is that during this phase, orbital energy will be converted into heat that will heat up the star and puff up its outer layers. If there is enough orbital energy, then the idea is that the envelope will be fully removed, resulting in a binary system that is very close together. If there's not enough orbital energy, then the black hole will meet the center of the star, and we won't have a merging binary black hole system. What can also happen is something called stable mass transfer. So instead of this dynamically unstable process, mass transfer is a more gradual transfer of mass from the star to the black hole. And in this phase, the separation can also decrease just enough for when the second star forms the black hole that they're close enough to merge within the age of the universe. So if we want to try to study how merging binary black holes form throughout the universe, then we have to simulate all of this physics for a universe worth of binary systems. So this type of physics ranges from many orders of magnitudes and many spatial scales. So this is a very difficult thing to calculate for millions and billions of binaries. The way that this has been done for the last 2 decades is to use binary population synthesis codes. And this diagram or this illustration is just to show that there's a lot of these codes out there. But the takeaway is that a good fraction of these codes rely on this BSE, binary stellar evolution code, that was developed more than 20 years ago. So there is this illustration that depicts sort of the state of binary and population synthesis modeling. And because a lot of these codes rely on this BSE code, it's turned into a kind of precarious situation. And the reason why it's a bit precarious is that these rapid binary population synthesis codes, in order to simulate these billions of systems, they have to make assumptions and simplifications to the stellar and binary physics. So one of these simplifications is that under the hood, all of the stars are pre-computed single star models. So even though these stars are in a binary and they're getting mass transfer removed or getting mass loss, under the hood, it's just single star evolution. And to determine these critical phases, like whether the binary goes through stable mass transfer or this unstable phase common envelope, this is not computed sort of self-consistently. It is, they rely on prescriptions that take sort of more detailed simulations and try to integrate them into these binary population synthesis codes. But these codes are very computationally efficient. So running one binary simulation takes fractions of a second. So with these rapid population synthesis codes, it was very frequently found that in order for a merging binary black hole system to be formed, it had to go through this phase of common envelope. So the way that I approach trying to understand the formation of merging binary black holes is by using the code called MESA. So MESA is a 1D stellar evolution code that solves the full stellar structure equations. And it's doing so during these emulated phases of mass transfer. So MESA simulates the interior structure of the stars, and we emulate mass transfer by removing some mass from the star, and that's supposed to emulate something like mass transfer and common envelope. So in this way, we're getting sort of the response of the star to these important phases of binary evolution. But it is much slower and more computationally expensive. So one simulation can take between 2 to 12 hours, depending on what evolution it's going through. But nonetheless, we wanted to compare these two different ways of modeling binary evolution. And what we compared was the evolution of mass transfer from a massive star onto a black hole. And we were interested in seeing how the formation of merging binary black hole would be affected. So here I'm showing a grid of simulations that was run with a rapid binary population synthesis code. It is for a 25 solar mass star and a black hole of varying mass. So the x-axis is the mass ratio of the system, and the y-axis is the initial orbital period. And here the colors correspond to the outcome of this binary evolution simulation, where the blue are systems that were too wide to form a merging binary black hole system within the age of the universe. And the yellow are systems that went through this unstable common envelope phase, but the black hole met the core of the star. So there's no merging binary black hole. But one of the takeaways here is that this distinction, this boundary between whether something is stable, so this blue system, and whether something is unstable and going through common envelope, the yellow is a straight line at a particular mass ratio. So this is a result of the approximations that have to be made in these rapid population synthesis codes. And another takeaway, like I had previously mentioned, is that all of the merging binary black hole systems were forming after this phase of common envelope. So if we take the same initial conditions, but now instead use these mesa-binary simulations, we found very different results. So first is the boundary between these stable and unstable systems was not this straight line at one singular Q, but it varied as a function of the orbital period, which now includes more of the stellar physics during these binary simulations. And the other main takeaway is that in this particular grid of simulations, the merging binary black holes were forming after just stable mass transfer. So we did not need to, a common envelope was not required to reduce the binary separation enough to lead to merging binary black hole systems. So this is just a grid of simulations. So we ran a few more at different donor masses and applied those grids of simulations to try to model a full astrophysical or a larger astrophysical population. And we found very similar results. So stable mass transfer can be the dominant formation channel for merging binary black holes. So in addition to this different pathway for forming black hole mergers, we found fewer binary black hole mergers in total once we wrapped these results into an astrophysical population, which led us to conclude that these rapid binary population synthesis codes might also be over-predicting the rate of merging binary black holes in the universe. So this was sort of to give you a bit of context for sort of not only has these detailed binary evolution simulations impacted the ways that we think about how merging binary black holes are formed, but it is drawing more attention to this stable mass transfer phase of evolution. So I'm excited to be talking to you all here today, because now that we sort of have established that stable mass transfer is important, there is a lot that we can learn about systems like X-ray binaries to try to deepen our understanding of binary evolution, as well as try to improve the modeling that we are using to model this key phase of stable mass transfer. So I wanted to talk about two sort of examples of how we can use this different population of binaries. And one of them, of course, relates to the spins of black holes. So in this sort of narrative of binary evolution, there are, we can measure the spins of black holes by inferring them from the gravitational waves of their merger. So sort of at this final snapshot. But with X-ray binaries, we can also infer the spins of the black holes at a different stage in their evolution. But when you compare the spins that are estimated and inferred from these two different stages of evolution, you find an interesting relationship where, so the x-axis is the spin of the black hole and the y-axis is just this CDF. And the yellow are systems that spins that are inferred from merging binary black holes, so with LVK, and the pink and blue are systems that are where the spin was estimated from either low mass or high mass X-ray binaries. So it's pretty clear that these two distributions are quite different. The spins from merging binary black holes are much smaller than those inferred from X-ray binaries. So a natural question is, can our binary simulations reproduce these two populations? Is there a problem for why these two distributions have such different spin properties? Or is there a way for us to reconcile these low spins of merging black holes and the high spins in high mass X-ray binaries. So it's quite difficult to form a high spinning black hole in high mass X-ray binaries. This is an open field of study. What we decided to investigate was a particular formation channel. I won't go through the details, but the idea here is that you have two stars that when they're both on the main sequence, they go through mass transfer. And this leads to the formation of a high spinning black hole, so that then it evolves to a high spinning high mass X-ray binary. So assuming this formation channel, we wanted to ask, can we reconcile these two different distributions? So we used the rapid population synthesis code to model this evolution and see what happens after this phase. So this plot on the right, each dot here is a binary system that went through case A mass transfer. So all of these dots we would assume are high spinning high mass X-ray binaries. And then again, I'm coloring the points with the outcome of the binary simulation. So the pink are systems that merged during the common envelope phase. So high spinning black holes, but it did not lead to a merging binary black hole system. And the light and dark blue are systems that were too wide to merge within the age of the universe. So again, highly spinning black holes, but again, no merging binary black hole systems. So this was with rapid population synthesis code. So we also wanted to incorporate our MESA simulations, but instead of simulating each one of these binaries with MESA, because that would be computationally expensive, we just took our grid of previous MESA simulations, and these black rectangles is the parameter space where, had we ran them with MESA, the binaries in those cells would lead to merging binary black holes. So we, of course, varied some of the physics, also looked at different different donor masses. And what we found was that the number of case A mass transfer binaries, so out of all case A mass transfer binaries, only 4% of them led to merging binary black holes. So out of the high mass X-ray binaries that we formed with high spinning black holes, only 4% led to black hole mergers. And then on the other hand, out of all of our merging binary black hole systems, only 7% went through this phase of mass transfer. So if we believe this case A mass transfer scenario, then this is a way to reconcile the two spin distributions. But I think the more important part for me, at least, is that this was a really great way to demonstrate how using multiple observed populations can be a very useful way to combine multiple points of physics and gain a deeper understanding of binary evolution. Another way that I wanted to demonstrate how we can use X-ray binaries to inform our understanding of gravitational wave sources is by trying to make better models for angular momentum and mass loss in a binary. And this relates very well to the talk that we just heard. So stable mass transfer, again, very important, but we're still making a lot of approximations in the way that we're modeling this in binary evolution. So one of these approximations is that the rate of accretion onto the black hole is limited to the Eddington rate. So if the mass transfer rate exceeds this value, then you have a lot of mass that is leaving the system. The angular momentum associated with this mass loss will be important for the long-term evolution of the binary's orbital period. What is currently assumed for how this excess mass leaves the system is that it is an isotropic wind emanating from the black hole. But as we just heard, this is not how mass leaves an X-ray binary system. it leaves in the form of these accretion disk winds that are emanating from the surface of the accretion disk. So what we did was to incorporate or try to calculate the angular momentum associated with these disk winds and see how it would affect the overall evolution of the binary separation. So what we did was we made this model for the angular momentum of the disk winds that takes into account the velocity of the wind around the disk and the velocity of the black hole around the orbit. We assumed a radial profile for the disk with this term zeta and calculated the angular momentum. So what I'm showing here is the ratio of the angular momentum rate from the disk winds compared to the angular momentum using the standard approach of this isotropic wind. The x-axis is the mass ratio and the y-axis is this psi term. Value close to 0 means the wind is pretty flat, and then a value closer to 1 is where more mass is leaving from the outskirts. And the mass ratio here is important because a very low mass ratio means that the black hole is more massive, much more massive than, or the star is more massive than the black hole. So the Roche-Loeb radius around the black hole that the disk has to live within is very small. Whereas in the high mass ratio case, the black hole is much more massive. The Roche-Loeb radius is wider, so the disk can extend to larger radii. And what you see is that this mass ratio has a stronger, dependence on this mass ratio than it does on this wind profile term. So now that we have these two different angular momentum prescriptions, I implemented them into our equations for binary evolution and calculated the final separation given these two different modes of angular momentum loss. So here the x and the y-axis are the same as before, but now I'm showing the ratio of the final separation with the disk model to the standard model. And for the entire parameter space, this value is less than 1, which means that this disk wind model results in tighter binaries. And for more than half, or for about half of the parameter space, this value is less than 2. So twice as small or even more. So now what I'm trying to work on is to implement this new prescription for angular momentum loss that is informed by these disk winds into MESA to simulate sort of what would be the results in the final outcome of the binary. How much would this affect the rate of merging binary black holes in the universe? So I'll leave my conclusions here, but in general, I'm very excited to talk to you all about black hole spins, disk winds, to see how we can improve our models for binary evolution. Thank you.
Thanks, Monica, for this great presentation. Do we have any questions?
Hi, I have some basic questions. First of all, in this kind of models, do you start from putting all the stars into binaries and then you let them evolve? That's one thing. And the second thing is, do you do any kind of tests how this evolution would change based on different environments like metallicity and so on?
Yeah, yes. So in all of these binary simulations, yeah, I'm assuming they're all in binaries. In these rapid population synthesis codes, you can just simulate the binaries, or you can also include the single stars, but the single stars won't lead to black hole mergers. And then your second question was, oh yes, the results that I've shown were just varying the metallicity from solar to 1/10 of solar. But to do a whole, the universe worth of binaries, you need a wider spectrum of metallicities. So that is also possible to do.
More questions?
When I start, so another very naive question, sorry. Not this clear. So from your simulation, seems like the result from MESA prevent the formation of some channel of the black hole binary hole, like the black hole merger. So some common element channel. And also combined with the wind model, the black holes will separate wider than the standard model figures. So these two results, could we just use these two results lead to the reduce the merger rate of the stellar mass black hole and reduce the final formation rate of the intermediate massive black hole?
Yeah, so I think your first point about preventing the common envelope channel, I wouldn't think about it as preventing. It was more, the way that I look at it is that previously it was overestimated how many of those would lead to common envelope. A lot of the time what happens is that when you are sort of in these rapid binary population synthesis codes, what is happening is that people simulate things in more detail, and then the results have to be kind of mapped onto these rapid binary population synthesis codes. So the infrastructure that is used there, and sometimes that mapping, I think, limits how precise you can be. So that is a way that I think you can lead to a sort of overestimating how many systems go through common envelope. And for the whether it's the disk wind versus the standard model, so what we found was that the disk winds will lead to smaller separations, not wider ones, but the point kind of still stands where, so common envelope will be a very effective way of shrinking the binary separation, but stable mass transfer is a more gradual process that doesn't shrink it as much. So comparing common envelope to stable mass transfer, we do go from sort of these very hard binaries to these wider ones that does reduce the rate of merging binary black hole systems. So we don't need to sort of invoke these disk winds to make that claim. But yeah, and then adding these disk winds to that picture might complicate things a little bit more. But that's just what we have to do to understand these objects. Yeah.
Hi, nice talk. I have a question. You mentioned super Eddington accretion, and that's when you added this more physical model of these coins. So how often is there a super Eddington phase in the evolution of these kind of binaries? Is it always, or is it, I don't know, what is the fraction?
Yeah, for merging binary black holes, it's very, very common. Like 100 times super Eddington. Where I'm defining super Eddington as just above the rate, the Eddington rate for mass transfer. So it's very common. It's not as common for other populations of binaries, but at least for merging binary black holes, it is. Yeah.
So I'm curious to think more with you about the things that are stable, right? And so as I understand it, there's that mass transfer is stable, but it's still not super long lived. So it might still kind of be a short episode relative to the stellar lifetime. But do you have a sense of what fraction of a lifetime it might be for one of those massive star binaries, and what that might mean about, like, could we catch mostly in stable mass transfer, we see things with like low mass donors that live forever, that kind of thing.
Mhm.
Not low mass extra binaries, but what would it take to catch some of these stable mass transferring systems and then compare their, say, period versus mass ratio diagram to those thresholds?
Yeah, no, that's,
Is that possible? Is the fraction too tiny?
yeah, when I've looked at these mass transfer sequences in MESA, the duration can vary from 100,000 years to like 2 million years. So there's a wide range. I haven't done the full statistics to see which out of that duration, which one is more common. But I think that's a really interesting question. So if mass transfer is happening, sort of, can we find it to see what is happening? Originally?
We might see these either as just like contact binaries, rotational filling binaries, if both components are stars, but if one's
Yeah.
a compact object, you might see them as X-ray binaries. Sort of. And could be worth thinking about whether you can like populate the two sides of that diagram with data. And then on the merger side, I think we're starting to figure out, and we can talk more about this, to probe what the mass ratio of the merger was from, say, a transient. And so there's some hope of filling in the other side of the diagram,
Yeah,
asking how that line that you drew kind of bisects this. I
yeah,
think that's super exciting.
yeah, no, we should talk more.
Thank you. More questions? If not, let's thank Monica and both speakers of today. See you next week.
Thank you.